Okay, this is a video answer key of the practice test for gases for chemistry. We're starting off with pressure equals force per area. So we just take 115 as the force divided by the area, divide those two and get 2300 pascals. A pascal is a Newton per meter squared. Second question, all we're doing is adding 273 degrees to our 35 degrees Celsius to get 308. Okay, next we're just going into the concepts. So if the pressure of a gas increases, the temperature must increase because the molecules are moving faster. Next one, if the volume of a gas increases, there's now more space for molecules to move. Therefore, the pressure decreases. The volume of a gas decreases, what happens to the number of moles? Well, the number of moles would have to go down then, because less moles means there's less space that the molecules need. Temperature of gas increases and the volume decreases. What happens to its pressure? Well, if temperature goes up, then usually the pressure will increase because the molecules are moving faster. If the volume goes down, there's less space, therefore pressure increases. Therefore, both of those cause an increase, so the net result is an increase. Temperature of a gas decreases. What happens to the volume of the gas? If the temperature goes down, the volume will go down because the molecules are moving slower. They don't need as much space. Okay, part 2, gas laws. First one, we have pressure volume equals nRT. Okay, the pressure of this gas is 88.5. The volume is 3.5 milliliters, or liters rather, because this is pure inert, you must be in liters. So that's equal to N, which is your moles, times 8.31, and of course 293 Kelvin. All temperatures must be in Kelvin. We get 0.127 moles. Now we have to identify the density of the gas. We have 4.07 grams. Well, we know that moles is grams over molar mass, so it's just a simple ratio. The molar mass is 32 grams once you solve that. 0.127 equals 4.07 over molar mass. The gas that has the 32 gram per mole is the diatomic oxygen, O2. All right, now we have more gas law calculations. Now we have a combined gas law, pressure 1, volume 1, temperature 2 equals pressure 2, volume 2, temperature 1. So then our pressure 95 multiplied by the milliliters, 45.5. Our temperature 2, since we're at STP, is going to be 273. And our pressure is 101.3 since we're at STP, times volume 2 times 303. A gas has a pressure of 55.6 at 50 degrees Celsius. We need our new temperature at a different pressure. So this is Gay-Lussac's law, pressure 1 T2 equals P2 T1. So 55.6 times T2 equals 77.6 times 323. And again, we have to get degrees Celsius in the Kelvin. Next one is Boyle's law. Pressure 1, volume 1 equals pressure 2, volume 2. We want a new pressure when the volume doubles. So 85.0 equals 66.7. Or times 66.7 equals pressure 2. And all I did was double the pressure. We're going to see that the volume causes the pressure to go down by a factor of 2. All right, now we have something collected over water. We have to remember that we have to subtract out the water pressure before we do this. We want to figure out the volume at STP. So with our new pressure, 85.36, once we subtracted water, multiplied by 99.5 times 273, because remember it's P1, V1, T2, once again the combined gas law, equals 101.3 volume 2 times 303. All right, next we have standard conditions, volume to volume. Okay, we're going to see the first 3 of these are just based on the idea that there's 1 mole over 22.4 liters. So if we just take a look at the first one here, if we go back up to our equation, there's a 1 to 5 to 3 to 4 ratios here. If you look at the first one, we have 25.6 liters of propane. Times that by 1 mole over 22.4 liters, because 1 mole of any gas at STP is 22.4 liters. Then you multiply it by the mole ratio of 5 to 1, and finish up with 22.4 liters of oxygen over 1 mole to get 128 liters of oxygen. Now the other ones are very similar, so we're just going to kind of glance at those very quickly. I'm going to go down to this bottom one. We have 18.8 grams of propane will produce how many liters of carbon dioxide at STP. Now this one, our first step, of course, is take the grams times by 1 mole over the molar mass. multiply by mole ratio, and then times that by 22.4 liters. And we get 28.7 liters. So see the similarities here? These are all the 22.4. Only difference is this side changes because we started with grams instead of liters. And notice how 22.4 liters stayed the same for all of these. All right, going on to the next one. Again, 14.4 grams of propane is how many liters of oxygen. 1 mole over the molar mass again, one more time, multiplied by 5 over 1, and then times 22.4 liters over 1 mole to give us 36.7 liters of oxygen. Again, this is just like the question above. The first step now is a gram to mole conversion first, and then a mole ratio, then ending up with 22.4 liters. All right, now we're not under standard conditions. So we have 32.2 grams of propane will produce how many liters of carbon dioxide at 160 degrees Celsius and 91.5 kilopascals. Now here we're going to do a gram to mole conversion and then follow up with a pivot when we're done. So 32.2 grams of propane times 1 over molar mass times 3 over 1. That's the ratio from the equation to get 2.2 moles. Using pivot, our pressure times volume. Our moles is placed there, 8.31, since we're in kilopascals, times our temperature gives us our volume. Okay, we're going to repeat this process for the next question. 13.5 grams of oxygen requires how many liters of propane? And the temperature and pressure are given. So one more time, this time we'll start with grams of oxygen times 1 mole over molar mass times 1 over 5 moles. That's the ratio. We end with moles. Follow up with pivot, PV equals nRT. And of course, 88.5, okay, multiplied by volume. And then our moles 0.0843 times 8.31 times our temperature 300 gives us 2.37 liters. So those two are very similar. Now we have gas collection over water. We have zinc and hydrochloric acid to produce zinc chloride and hydrogen. Okay, so the first thing I do is I take my 97.5 kilopascals and I subtract my water pressure to get my pressure. The next thing I do, a gram to mole stoichiometry between zinc and hydrogen. 0.075 grams of zinc times 1 mole over molar mass times 1 over 1. It's a 1 to 1 mole ratio. There's my moles. I'm taking my pressure, 94.2, taken from here once the water's taken out, times volume. Again, we're using PV equals nRT. Placing my moles from there into here, times 8.31. That gives me times 299, which is the temperature. I get a volume of 0.0303 liters. Now I times that by 1,000 milliliters per 1 liter to get 30.3 milliliters. Now to get my percent yield, I take, well, actually I got 27.4 divided by what I'm supposed to get by stoichiometry and times by 100 to get 90.4%. Now limiting reactant stoichiometry is next. We're going to just do volume to volume this time. We have 56.3 milliliters of butane reacts with 85.5 milliliters of oxygen. I strongly suspect oxygen being the limiter because we need 13 amounts of oxygen for 2 of this. And I can see that that's not true there. We don't have that much. So I'm taking 85.5 milliliters of oxygen. And again, times 1 mole. Now this time I'm dividing by 22,400 milliliters instead of liters, since I'm in milliliters. I multiply by the mole ratio of 2 to 13, and then one more time, I'm multiplying by 22,400 milliliters of butane. I find out I need 13.2 milliliters of butane. I look there and I see I've got 56.3 milliliters. I've got way more than I need. This tells me how much I need. So oxygen's a limiter. Now I run the limiter to find my product, which we want to find is carbon dioxide. 85.5 milliliters of oxygen, again, times 1 mole over 22,400 milliliters, because I'm in milliliters. Multiply by the mole ratio of 8 over 13 for oxygen, times 22,400 milliliters of carbon dioxide per 1 mole. And I get 52.6 milliliters of carbon dioxide produced. Remember, I have to use my limiter through. If I place my excess through, then I will overestimate how much is actually produced. Now to get our excess, I'm taking my milliliters I was given, I'm subtracting the milliliters of butane needed, and that's my excess. Last concept covered is Avogadro's principle. We have 3 different balloons, all at the same temperature and pressure, or 4 different balloons. Nitrogen and oxygen are the same size, chlorine's the smallest, and hydrogen's the biggest. So the chlorine gas has the largest mass. Possibly it's got the heaviest atomic mass, but we don't know its exact volume, so we can't know for exactly sure on that one. Next statement. Hydrogen gas has the most molecules. Yes, it's got the largest volume. According to Avogadro's principle, Since they're all at the same temperature and pressure, the one with the largest volume would have the largest number of moles. Next question. Nitrogen gas has less mass than oxygen gas. Okay, they are the same volumes, therefore they have the same moles. Nitrogen has a lower molar mass than oxygen, so that's a true statement. And last but not least, the chlorine gas has the least amount of molecules. Yes, it does, because it has the smallest volume. And that's our review, okay, our video review for our test.